Stone, who will tell us about localization of the path interval in certain theories. And the presentation will be in Russian, right? No, I'm sorry. Maybe.
But of course, we can hold. Let's hold. So think English.
Okay.
Okay. Swedish. So it's the last lecture, so let me just maybe sketch a brief plan so that I wouldn't forget what things I should mention. So first, I should sell general localization. It's a statement, maybe not theory. It's formulated by Witten. Second, I will tell you application of localization applied to computing indices of operators, equivariant indices of operators. That's ITS. Sorry, I'll tell you about more concrete things. We'll consider gauge theory. Theory UN on R4 it subscripts epsilon 1, epsilon 2, which means that it's equivariant with respect to the rotation. I'll tell you later. And I'll tell you a bit on gauge theory on S4. So that would be enough. And finite dimensional example of localization. One-dimensional concrete example of the stuff that was yesterday. Okay, let's hope I'll cover these subjects. Okay, so let's do finite dimensional example. Okay, so we had a system when we have equations equal 0, mod symmetries. And we want to lift that to the bigger space, okay, from this set. Let's consider the example. Take C2, Z1, Z2. It's a historic example how you get P1 by symplectic quotient. So you take moment map Z1 squared plus Z2 squared. Standard symplectic structure here. So you get P1 action from this associated to this moment map, which rotates Z1 to E phi, Z2 to Z2 E to phi, right? And to fix, if we fix mu equals R and divided by P1 action, so what we get is CP1. Okay. So what we did yesterday, it was a representation of an integral over CP1 on some differential form. Yesterday it was shown how to lift that integral over CP1 to the bigger space, in this case C2. We multiply by symmetries, by those U1 symmetries, and we go away from the set of zero sections of these equations, that the radius is fixed. Okay. So I'll not give you all concrete formulas, but I'll tell you the structures, and you can practically check how it works.
Can you think of this as idea of T?
No, it's other way around. It's other way around.
No, I mean when you started from integral over CP1 and ended up with integral over C2.
Well, it's similar, but it's a bit other way around. You'll see in a second. In Faddeev-Popov case, you have so here to go to the integral over C2, you'll use the equivariant multiplet, which has two scalars, lambda and phi, and one fermion eta. In Faddeev-Popov, you usually have CC bar. So we have lambda and phi bosons, and this is fermion. That's us. And Faddeev-Popov they have what they call the CC bar, right? CC bar and B. And B is boson, CC bar fermion. It's like inverse to Faddeev-Popov. It's like going in other direction. Faddeev-Popov, you restrict the integral of a big space to the integral of a gauge fixed slice. And instead of doing that, we lift the integral from.
No, this is what I said. It just.
Yeah. So it's just opposite statistics. So, but this is because it's very parallel. So let's see what would be the fields here. Representing this integral. More exactly, it's not just the integral over C2. It would be the integral over the bundle of C2, which the bundle of equations. The equations are just those equations. Anyways, now let's go concrete. So the coordinate multiply. Yesterday it was a mu and psi mu. So today it would be zi. Okay, and so q zi gives you cube psi, and similar with bars, and q psi gives you, let's say, minus phi zi. This is equivariant differential acting on the C2. These coordinates z1, z2. Okay, that's coordinate multiply. Next, we had that equation multiply.
Sorry, what is phi zeta? Is it what, subscript? Or?
No, phi, I'm writing q as Durham differential minus iv phi. Phi is the field.
Okay.
Phi is the field. Phi, in our case, phi is just a scalar, real scalar. In principle, it is an Lie algebra of U1. So it is just a real number. So this coordinate multiply q is a Durham. Okay, that should be very clear. Equation multiplet. Equation multiplet is a trivial bundle, R bundle with bundle R over C2, whose fiber is where moment value takes where moment takes value. Just the Lie algebra of U1. So for equation multiplet, the usual notations for the fields was H and chi. Okay. So we take Q on H is chi, and Q on chi is 0 because they are invariant under the Durham differential. So here chi is in projective parity inverse R, and H just a real number. And finally, we have the projective multiplet.
H is a scalar field.
H is a scalar field, zero-dimensional field. Sorry. Yeah. Projective multiplet. For those we had that, you remember, lambda and eta. So Q lambda is eta, and Q eta is 0. So lambda is again a scalar, and eta is a fermion, real fermion. And we have the separately standing phi, Q on phi 0. Okay, everything's clear? Good. Well, here for coordinate multiplet, the same formula is called for zi bar. Just for bar, you would change minus to plus here, right? Because under U1 action, z bar rotates in the opposite direction. So that's the multiplet, and now the action. Now recall how we constructed the action. So first of all, we had S equations plus S projection. Then I also added S equivariant last time, but in this case it's not really needed because the group is abelian, but it should work like that. So S equations, we take Q. Now it's chi contracted with, we need to take that auxiliary field H minus section. So for the section, you take this Z1 absolute value squared plus Z2 absolute value squared minus mu. I keep the value of the moment map denoted the same letter mu.
Now this is just numbers.
Yeah. So we will, in the end, this integral will be the integral over these psi h chi lambda eta and phi. Okay, and that integral reduces to the integral over CQ. So this is as equations Q of Z, and as projection. Well, it's Q of this Q of eta. You remember, as projection supposed to give us a volume form in the fiber directions. So let's see what are the fibers here. The fibers are, if I change coordinates, go to polar coordinates, say r1 phi 1 and r2 phi 2, then the fibers are generated by vector fields d phi 1 plus d phi 2. Right? Those circles. So here we'll take corresponding to that vector field the one form r squared d phi 1 plus d phi 2. So what I write here is just the one form which I obtained from this form using the standard flat metric. Make sense? That's it. So the claim is that the integral over CP1 of anything, I mean of a differential form, of closed differential form, is integral over d phi straight phi, the one which was in the multiplet. And this is curly phi, this is angles, not to be confused with straight. So integral over d phi, and then the integral over coordinates of C, so that's dzi bar, d psi I, d psi bar, integral over h and chi, dh, d chi, and integral over h fixed and multiplied, d lambda, d eta. E to minus s, where the action is this. So we have limited time. I think I not tell the details well, but this is discuss this if you want. So let's move to next. Are there any questions on on this example?
This is not the usual CPN model, CP1 model.
This is CP1 model. It's a usual. It's a usual. Well, look, it's what is called gauge sigma model. So what is here? It is a gauge sigma model in 0 dimensions. The worksheet is 0 dimensions. We are doing just finding dimensional integrals, and you can extend it to 2 dimensions, and then the reduction which happens here is how you go from gauge sigma model to sigma model on symplectic quotient. It's exactly the same process. That's familiar to physicists.
So this is in 0 dimensions.
This is a relation between gauge sigma model and sigma model in 0 dimension, exactly. And it fits into that formalism of localization. You can actually concretely see why one integral equals nothing.
And that is the dimensional reduction of the one in two dimension?
It's dimensional reduction of 1 and 2 dimensions. Yes, it's zero-dimensional version. Yes.
Written as this is kind of strange that you don't have an alpha on.
Yeah. When you started asking question, I looked on there and noticed that. Right. That's right.
But just to understand, alpha on the left-hand side is a function of x and psi, right? So you understand as an integration with differential form.
It's a differential form, right?
So, but on the left-hand side, the integral will be over d zetas, coordinates on this, and
so you take alpha, which is a closed differential form upstairs, and you restrict it.
So you want an equivariant guy on the right.
You want equivariant guy.
And then you get the alpha on the left.
That's right.
no, right. But I'm asking, did you introduce fermionic things for the differential form?
Well, here I didn't introduce them explicitly, but I just understand this as an omega of CP1, and not as a function CP1, but as an omega. Okay. Any other questions? But this is concrete computation that you can make. If you're interested, and check as it works. Okay. So we did that. Now let's see. General localization statement. We can talk about localization and different mathematical theorems and equivariant classes, cohomologies, and all that stuff. There is a very simple picture that can be applied in any situation about localization that I know. Just it has to be worked out, but then it's true. And the statement is very simple, sounding simple. So given a supermanifold, like this, the space of all fields in your path interval, bosonic and fermionic, and you want to integrate over that supermanifold something form alpha. And let's say that Q is a vector field, is an odd, Q is an odd vector field on M such that Q squares to 0. Like a supersymmetry generator. Then, and let's assume, and also let's suppose that Q alpha equals 0. Now first, assume that Q doesn't have fixed points on M, if Q acts freely. If Q acts freely, then you can introduce a coordinate theta in the direction of the Q action in that fiber. And when you integrate over theta, you get 0, because alpha doesn't have theta in it. The integral d theta alpha gives you 0 because alpha doesn't have theta, that coordinate corresponding to Q action. So, integral of any such form alpha would be 0 if Q acts freely. So suppose now that Q doesn't act freely. What shall we do? Well, let's just consider a local neighborhood of a fixed point of Q. Take fixed point of Q. Cut your manifold in the orbits of Q, and the integral away from the local neighborhood of that point gives you 0. The only non-zero contribution comes from arbitrarily small local neighborhood of a fixed point of Q. So that's the statement. So you can reduce or localize the integral over the whole supermanifold of Q closed form alpha to the integral over fixed points of Q. Let's call that subset F, restriction of the form to F, and then you multiply that by some measure on the subspace which comes from the what we call one loop determinant. You need to integrate the fluctuations of your fields in the normal directions to that fixed point, and you get any kind of localization formula that is known in doing this formalism. Any questions on that? Yes.
Does this require some metric on your space of fields, this argument with that you only get contributions from the fixed points of Q? If you have a theory with a Q in it, but you don't have any notion of a metric, does the argument go through anyway that the theory will sit on the fixed points of Q?
I think it does. You can introduce metric to prove this argument, but it's an auxiliary tool to prove it. No?
I mean, imagine your Q squares to Lie derivative, and Lie derivative is not the action of the group, then you don't have invariant metric, right? Then you wouldn't be able to really prove this statement. I mean, heuristically it goes through sort of, but...
So it's heuristic statement. I'm sorry, I'm not claiming this is mathematical statement. It's a heuristic statement which I give in addition to all more or less mathematical statements.
I don't see the complication here. You're just doing the same thing you did before for a node, for a supergroup instead of for a group. Right. So this is a
No, right.
I don't see any
But I
complication.
think Johan's question is the following. Imagine you have a Q which doesn't come from the group action. So, for example...
But he's using a Q that squares to 0, right? So this is not part of his formalism.
I mean, we can skip it. I mean, it's heuristic, but there is a loophole in this argument.
Well, I'm not proving here, but still. Well, okay. I think we got opinions. We can move on. But anyways, so this is how you describe all localization statements which are known precisely. They all fit in this formalism. I'm not saying that you can derive maybe something else, but generally, that's what it is. Because how it works concretely in different situations here, sometimes it does, sometimes things are more involved. So, but anyways, for physicists, this should be a perfectly clear picture of what localization is about. It's localization to the zeros of fermionic transformations. Like if you have a system of bosons fermions, blah, blah, then you set, and usually when you write you on your fermions, and here are some equations on bosonic fields. Usually it's some PD. So where Q has zeros is the points where those equations are satisfied. That's how Poincaré-Hopf theorem worked in the first lecture. Okay. Yeah, time is fine. So let's do now indices of elliptic operators. Transversal elliptic operators. Indices of transversal elliptic operators. So suppose I have a manifold and vector bundles, let's say E over M, F over M, and suppose group G acts on E and F, and I have a differential operator from sections of E to sections of F. Which is compatible with the action of G group. So D and G commute. Okay. So just you know, take a familiar whatever example of differential operator and take a group G such that the differential operator is invariant under the G action. So, and then what you want to define, index of all operator. In the usual situation, index of operator is just the dimension of kernel minus dimension of co-kernel. In the equivalent situation, we want to treat the kernel of D and co-kernel of D as vector spaces, as a modulus of G, as a representation of G, because G acts on kernel and co-kernel because of the definition. So equivalent index, let's say with respect to the group G of operator D, we define it as a character so we define it as a character. Well, it's better, it's easier to write it as I take this index. This index, it's easy to think about this index as a function on Lie algebra of G. So if I evaluate it on some element U from the Lie algebra of G, I get defined as a character of a kernel of D e to U minus trace of co-kernel D of e to U. This definition makes sense fully for transversal elliptic operators, in which case those for elliptic operators, they are frequent, so kernel and co-kernel are finite dimensional, and what we get here is just a difference of two finite dimensional characters, so just a function on the algebra of G. In transversal elliptic case, those would be non-functions, but Atiyah proved they would be distributions. So more precisely, if you expand those characters in the irreducible representations of G, then each reducible representation appears here in the sum with finite multiplicity. And it's possible to compute those multiplicities precisely. Okay. So the formula is, now let's take simple situation. Assume that G, let's say G is U1, and fixed points of G action on M are discrete. So let's say that F is the set of fixed points. And Atiyah's singular localization formula for the index index formula is that the index, the equivariant index of transversal elliptic operator D is the sum over all fixed points, say point P in the set of fixed points. And then, like it was last time, there is numerator and denominator. Numerator comes essentially from just fibers of those vector bundles on the point, and that numerator and denominator comes from the one-loop determinant. Well, so I'll write formula in a second, but I'll tell you how you derive it. To derive it, you would consider twisted quantum mechanics in twisted quantum mechanics with target space this target space M, so you do path integral over the loop space of M, and from the determinant near the fixed points in that quantum mechanics path integral, from that one loop determinant, you will get what I'm going to write.
How in quantum mechanics this operator will appear, just roughly? I know many examples when you will have Dalbu, etc. But
Right.
generically, can you say it?
Generically.
Yes. I mean, how, if I would like to.
Yeah, I think I can, but maybe later. Okay, so let me just finish writing down the formula which you will use for practical applications. The formula is in the numerator, you just evaluate the character on the fiber. Now, here we want to compute the difference of character on the cohomologies, and here we just evaluate it on the fiber, that is on like on one point of those sections on one point. So it would be trace over fiber. So trace over fiber of vector bundle E in the point P of E to U minus trace over the fiber of vector bundle F in the point P of E to U. Okay, and you divide it by the determinant taken in the vector space, in the tangent space at the point P, tangent space to the manifold M, of the operator 1 minus U. So where I mean that, well, here we take, maybe better to say that this is a representation with which U acts on the tangent space at the point P. Okay. So that's the beautiful formula, and I'll show you how it works just in a few seconds. We'll do step by step, starting from simple examples and then more complicated. Like Riemann-Roch, Hirzebruch formula, etc. for Euler characters, vector bounds can be seen as particular case. Well, of course, this has a generalization when the fixed points are not, the set of fixed points are not points, but some subspaces of the manifold term. Then you replace what is written here essentially by Todd class or by a root genus, right? ITS Singer theorem for Dirac operators. But again, you can derive all these theorems from as physicists you would write down quantum mechanics. This is quantum mechanics with parts. All right, let me show how it practically works. So consider C and operator D bar. So what would be, and you want action on C, let's say coordinate Z, and it acts by sending Z to TZ. Alright, let's compute index of the operator. Local contribution to this index near the origin, near the fixed point. The fixed point P is Z equals 0. Okay. So let's first compute index using this formula. So we have the differential operator D from from 0,0 forms to 0,1 forms, right? So these forms are like FZ bar, VZ bar. We would need U1 action in the fiber of 0, 1 forms to write down this number. So it's going to be 1 because it's trivial weight when you want x on scalars. Minus t to minus 1 because this is 0, 1 forms. That's numerator, square, and denominator. Denominator is determinant of operator 1 minus representation of the tangent space. So the tangent space is z bar, and you want x with the weight t on z, and with the weight t to minus 1 on z bar. So what we get here is 1 minus t, 1 minus t to minus 1. So happily, the formula simplifies greatly. You cancel that, and we get 1 over 1 minus t. And it's also useful to represent it as an expansion in powers of t. So this is the sum from 0 to infinity, t to the n. What is interpretation of that? So first of all, recall how we defined the index. The index we defined as a difference of traces over of the characters between the kernel and kernel. First of all, what is kernel of this del bar operator? Well, we have Poincare lemma, which says that for any object here, there is an element in this space such that del bar of this guy will give you that one. So co-kernel is trivial. There is only kernel in the question, and the kernel is the space of local holomorphic functions near the origin. So holomorphic functions f of z, well, it's we expand them over all powers, over all positive integers. And that's the space of holomorphic functions is U1 module. You want x on the space with weights n in positive integers, non-negative integers, multiplicity 1. So you see it exactly agrees with the index computation you've got there. Yes.
If I would like to recover a normal index from equivalent, do I know?
Normal index from equivalent, yes, you would just set your group element to 1.
Okay, so this traces
Because
just will be traces
it
of
would be just
identity.
infinity.
Right,
Right.
not in this particular case, but in general.
In general.
If index is well defined, I will take
If
the trace.
it is well defined, you will just take u equals 0. You compute that function, you cancel all numerators, denominators, so like artificial poles here, this is artificial pole. You cancel all those and you get, actually you'll do this in a second. Let's do it for O1 bundle over CP1. Okay, we're gonna recover we want to see that there are n+1 sections. So, sorry. Right, so I want to do that equivariantly. So I consider C2, the space C2, is coordinates Z1, Z2, modulo Z1, Z2 identified with lambda Z1, Z2. So this is this direction. Oh, as you know, we get CP1 using such quotient. So and I want to compute the index of del bar operator on ON bundle of on top of CP1. So how would do that? So you get the total space of ON bundle if you take the coordinates Z1, Z2, and for the coordinate in the fiber take Z3 and take the action that when Z1 so Z1 goes to lambda Z1, Z2 goes to lambda Z2, Z3 goes to lambda to the power n Z3. It corresponds to O n lambda. So what you have, dw over w here, w is in U1, so it's a contour integral, and it's used to average over the equivariant, under that identification. Now we just need to write down the fixed points on the space. It would be w to n, it comes from the numerator, and 1 minus t1 to minus 1w, 1 minus t2 minus 1w, so if you compute it by residuals, you'll get t1 to n over 1 minus t1 over t2 plus t2 to n 1 minus t2 over t1. So parameter t2 over t1 is what you would call just the equivariant u1 weight when it acts on CP1, the ratio of those guys.
So Vasily, what are we doing now?
What are we doing now? We compute the index of Delbo operator on CP1 in ON, twisted by ON long band.
Why did we start with this contour integral?
Oh, sorry, contour integral, we just want to average over the U1 action on C2. Well, there is another U1, I'm sorry. There is one U1 which acts on CP1, and the weight of U1 action on CP1 is given by T1 over T2. There is another U1 as game, which is a compact subgroup of that C star action on C2. That's confusing?
Yeah, but it's not U1 action on CP1, right? I mean,
Which one? This one?
No. There is by itself U1 action on CP1, right?
There is by itself U1 action on CP1. It's represented by T1, T2. There is another thing, W. It doesn't act on CP1. CP1 is obtained by quotient from C2 by C star action. And W is an element of this C star.
But it's just trick to write the answer a priori. I mean, if you look at this theorem, I mean, you have just line bundle over CP1,
yeah,
and that's it. And then you count the fixed points.
Exactly. You can look at it as a trick. So if you're confused by all that, just forget about it and apply a singular localization fixed point formula to CP1. Okay. So what CP1 has? So CP1 has two fixed points for U1 action. The parameter that U1 action is T1 over T2 in this formula, North Pole and South Pole. And I've just written the what we have computed in the previous example, index of Delbo operator near the North Pole and near the South Pole. And the numerator comes because of twist.
So you mean that contour integral over W will automatically pick up all the fixed points?
Contour integral picks up fixed points. Fixed points. That's right.
But naively, I would think if you draw the contour at this equator, it would either take up the one in the North Pole or in the South Pole, but not both, right?
No. For expansions for Dolbeau operator to make sense, you take absolute value of t's less than 1. You remember we had the series 1 over minus 1 over t, and we expanded in positive powers of t. So you think about t formally, that absolute value of t is less than 1. But for w, you take w integrated for w absolute value equals 1, so it picks poles inside the circle. It picks both poles. Well, if you're confused, sorry, I don't have time for that. Okay, come on. So if you now take that, what happens if you multiply that by t1 over t2? You get the same numerators here, but with a reverse sign. So what you get? 1 minus t1 over t2. Here it will be t1 to n minus t2 to n, t1 over t2. So then just expand that in there should be some, the answer is going to be t1 to n plus t1 to n minus 1, t2 to 1, blah, 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 plus t2 to n. Maybe I made a mistake somewhere in the algebra, but conceptually you get it. Every term in this polynomial represents a section of ON bundle. There are n plus 1 sections, and these are equivalent weights of those sections with respect to t1 over t2, well, twisted by also overall power.
But now if I go to normal version, I have to put t1 and t2 to 1, but I will get too many terms.
No, you'll get just n plus 1. You put them to 1, and you get that this sum equals n plus 1. And this n plus 1 is the index of the Dolbeau operator twisted by O1 bundle. You see that there are n plus 1 sections.
So these are just power z1 to the power n, the 2 to the power.
Yeah.
And each of them has
Yes,
weight.
exactly, precisely. Good, gauge theory on R4 epsilon 1 epsilon 2. I'm not sure, I have like 10 minutes to explain a Nekrasov function, 5 minutes to explain theorem S4. Or other suggestions? What shall I do with that to explain this thing? But we have to understand those indexes to talk about gauge theory and computing the pattern.
Maybe it will be nice and to watch extra 10 minutes.
Another extra 10 minutes, you mean?
Yeah.
Okay.
Never. So, gauge theory. UN on R4 epsilon 1 epsilon 2. Let's see. So let's start from the simplest, because I want to have a continuous interpolation between what we've done so far. So, write down the Donaldson complex which I had at the end of the last lecture for the gauge fields, scalar fields, Fermions, etc. for n equals 2 twisted theory, the one which is about the one which lifts geometry of instanton modular space to the path integral. Okay, let's do it formally for U1 theory. So there you can show that the path integral reduces to the fixed points of the Q operator, to the modular spaces of self-dual connections. Well, for U1, we don't really have self-dual connections at this point. I'll show you them later. Let's just compute the partition function near the trivial fixed point, near all fields, set all fields. Take the fixed points where all fields equal to 0. The simplest fixed point. Well, I have actually to tell you what we are doing. Well, what we are doing. We have the manifold, the space of all connections. Okay, let's call it space of connections. You have group G, which acts on the space of connections, and we consider quotient. On top of the space of connections, we have that bundle omega 2 plus value in a generator G. So those formulas with Tom classes and projective forms, which we insert on which we interpret as the path interval measure in the vertical directions of the fiber, give us in the end the formula. So the integral of e to minus s, and that's n equals to twisted, right, is the same as the integration of the space of all connections, mod G, the Euler character of the bundle of the self-dual two-folds. Okay. Now use Atiyah point fixed point theorem. So, and consider it near trivial fixed point. When all fields are zero.
So what fixed point on the which action? I assume
oh, yeah, on the which action, right. Exactly.
We didn't introduce any
I forget to tell, yeah. So we consider the space of all connections. Let's say on the manifold on R4, and I put epsilon 1, epsilon 2, which means we treat it equivariantly with respect to SO4, with respect to U1 to power 2. Action on R2, I split the R4 space in two planes, and U1 acts with the weight, with the e to I epsilon on z coordinate in this R2, and e to I epsilon 2 on z coordinate in this R2. Okay. So what we are doing here, we are computing the differential form here is representative of equivariant homological class of that guy. This is what follows from that story about Tom classes and projective forms. So what we are computing here, we are computing the Euler character, and I put subscript t here. It's equivariant Euler character, where t is this U1 squared group acting on all those spaces.
I'm confused. This little g in this bundle, so this is a bundle over a nice modular space now, right? And
so far, no, this one, this is bundle of the space of all connections.
Oh, so we're not...
No, it's not finite dimensional.
We're not modding out them by G, or I don't understand.
We do modding out them by G, but it's still infinite dimensional space.
But the resection of the group coming from R4.
Sorry, I'll answer the question. B curly A is the space of all connections on R4.
And big G is here gauge transformation.
Gauge transformations. Okay, when you mod out, you still have like 3 functional degrees of freedom, right? So good. And we integrate all the space equivariant Euler class of that bundle of self-dual two forms valued in IGN G. Okay. Now use fixed point theorem. One fixed point theorem with respect to the T action on the space. Okay. One of the simplest fixed points is just all fields are equal to 0. So Atiyah point fixed theorem. You take all fields equal to 0, which means here an exponent you have 0. So exponent to 0 is 1. And then you divide that by the product of weights which appear in Atiyah bot formula, that equivariant Euler class. Okay? So it's equivariant Euler class of the tangent space to A mod G. So that would be equivalent Euler class of omega 1 adjoint G. And since we have quotient here, the tangent space to the group goes to numerator. The numerator you have equivalent Euler class of omega 0 adjoint G. Okay. So far what I have written here only denominator. It was denominator in ATIA both fixed point formula. And still you have to write down just this observable which you have on the left. So numerator also have equivalent Euler class of the bundle of self-dual forms over the space of four connections. Valued in adjoint G. And now I should actually raise that integral. It's an integral of the space of fixed points, but here we just consider contribution from point all fields 0. Okay, that's what this equation is. It's one term in the sum over fixed points. So and now I want to compute this term, the ratio of those equivalent Euler classes using ATIA Singer index theory. Remember what equivalent Euler classes are. They're just a product of weights. So we want to find the set of weights of T action on those spaces and multiply all those weights. And there would be lots of consolations. It's convenient to do that using the same insight from the H theory. You have the self-dual complex associated to this formula, naturally. It comes because they came from the equations, and the equations were F plus equals 0. So what we have, the complex which is associated to the ratio is the complex of self-dual operator from the space of functions on the manifold M, differential gives you a local gauge transformation in tangent space to the gauge transformation. This is the space of connections. And operator here is D and then projection to the self-dual two forms. This is to the space of self-dual two forms. And everything is valued in G. Right? This is like deformation complex for the module space of self-dual connections. Okay. And I just consider tangent space. So we're going to compute the ratio of Euler product classes by converting the differences of the Chern classes, right? Because Euler classes are multiplicative and Chern classes are additive. So you want to compute Chern class of this guy. Well, it's like the index of the operator, but except that the sequence here has 3 terms instead of 2 terms, but it's defined in the same way. We sum over all terms here with -1 raised to the degree of the appropriate guy. So let's do that. So T acting on R4 has fixed point zero, and the weights, and we need the weights of T action on the fibers of those bundles. Okay, so let's just write down the weights. Here the functions have trivial weight. So Tx by 1. Connections, the space of connections, one form, so dual two vectors, 4-dimensional space. And the weights of T, well, T is generated by T1, again, T1, T2, where T1 goes like Z1 to Z1T and Z2 to Z1 to Z1 T2, Z2 to Z2 T2. That's how T1 and T2 act on the coordinates, complex coordinates on C2. So weights on omega 1, on the fiber of omega 1 in 0 will be T1 to minus 1, T2 to minus 1. Clear? Because just the tangent space, Z1 bar, Z2, Z2 bar. So what are weights on self-dual 2 force? Well, self-dual 2 force is three-dimensional, and this torus, as you can check, well, the self-dual 2 force, I will say concretely, it is spanned by dz1, dz1, dz2, dz1 wedge dz2 bar, and dz1 wedge dz1 bar plus dz2 wedge dz2 bar. So what are the weights of T1 of U1 squared action on those spaces? They would be T1, T2, T1 to minus 1, T2 to minus 1, and 1. This one doesn't transform.
I'm confused with this new torus appearing here. We started with an action of U1 on fields by putting this action of U1 on R4 with this epsilon 1 and epsilon 2.
That's right.
And we already took fixed points of that action. And now we're looking at an action of a different torus.
No, the same torus.
But this torus is U1 cross U1. So.
And we consider torus U1 cross U1. Maybe I missed your question.
Oh, I thought the action was from T, that it was acting as e to the epsilon 1 T on one guy.
It's the same.
Okay.
It's the same torus. Maybe I confused some words, but it's the same torus. We take U1 squared.
Okay.
It acts on R4. That action is pulled to the action on the fields.
Okay.
And
And
we are
now
talking
here
about
we're
this
forgetting
action.
about the epsilons then. Okay, so I
Oh, sorry, epsilons.
U1.
I'm just using the notations where T1 is e to I epsilon 1, T2 is e to I epsilon 2.
I see. I thought that originally this was the action of a single T into
Oh,
different copies of C2. Okay, okay.
Yeah, okay, good. So far should be clear. We just computed what I deleted here, but we computed numerator in a T-Singer formula by computing the weights on the fiber of those bundles at the fixed point 0, at the origin. So now we'll compute the chair class of this complex by writing down actually the T-Singer fixed point formula. So numerator is going to be, we take this plus sign, this guy and that guy. So it gives us 1 to 1, it gives us 1 plus 1, I write explicitly always T1, T2 plus T1, T2 to minus 1. Okay, minus the middle term in the sequence. So minus T1 plus T1 to minus 1 plus T2 plus T2 to minus 1. Okay. Denominator is the product of weights on the tangent space of R4. So the tangent space to R4 has Z1, Z2, Z1 bar, Z2 bar. It's essentially the same weights, and just those four. So we take products of 1 minus those four weights. 1 minus T1, plus T1 to minus 1, minus T2, 1 minus T2, minus 1. Now, you can simplify it. You can simplify it to, it's 1 minus T1, 1 minus T2, 1 plus T1, T2. The reason for the simplification is just you can actually view this complex as a twisted, as a del bar complex, twisted by 1 plus canonical bundle. Okay. So 1 plus canonical bundle give you 1 plus T1, T2, and del bar gives you 1 over 1 minus T1, 1 over 1 minus T2, just by the same argument we did for del bar operator on C. On C line. Here it's on C plane, therefore denominator has 2 factors. Is it clear? Okay, now we convert Now, we wanted also those weights to be taken in adjoint of G. So let's actually multiply this by the character in the adjoint of G. So you have to put here the sum over roots. Okay, e to alpha. Sum over roots alpha, e to alpha. So let me actually expand that in the powers of t to see the multiplicities. So it would be the sum over n1 and 2 greater than 0, just representing the expansion powers of those two factors. And then it's e to I n1 epsilon 1 plus I n2 epsilon 2 plus that comes from this factor, from this term, and from that term that would be shifted by 1. If there is any confusion, I'm just using this relation between t and epsilon. So plus I and 1 plus 1 epsilon 1 plus I and 2 plus 1 epsilon 2. And also there is a sum over roots. So plus alpha, where alpha is a root of G. So this Chern character, it's all one line. So this is the Chern character. And we now see all multiplicities, well, multiplicity is just trivial, all multiplicity 1, but we see all the weight spaces of so actually I forgot to say why we are doing this, why we are multiplying by e to alpha. I just wanted to consider that the Chern character equivalently with respect to the T torus section and the torus section corresponding to maximal torus in G, in the gauge group of the theory. So given that we know the Chern character, we can compute the Euler equivalent Euler character just by taking the product of weights. The ratio of Euler characters, which was here, because of multiplicativity property, is precisely the product of all weights which appear in the Chern exponents here. Okay. So the contribution from 0 fixed point to z, I call it like the 0, is the product of all these guys. So it's product of n1 and 2 greater than 0. Let's say that element from Lie algebra of that maximal torus in G, element in the carton of G, I evaluate the Chern character on that element. So it's alpha contracted with A. I want it. Yeah. I want to evaluate it on A. So then this product gives you product n1 epsilon 1 plus n2 epsilon 2 plus alpha A, and the same where n1 is shifted by 1 and n2 is shifted by 2. Well, this is an infinite dimensional product, but after realization by zeta function or whatever, you get what is known as Barnes double gamma G, double Barnes gamma function, gamma 2 of alpha of A with parameters epsilon 1, epsilon 2. You can just think about the term, this product, as a definition of this function regularized. The point is that it has poles in the two-dimensional lattice spanned by positive n1 and n2, and it generalizes a product formula for inverse gamma function. And from that term, we get the same guy, but it's shifted by epsilon 1 plus epsilon 2. Okay, so what we have computed so far, we have computed the contribution of the trivial connection to the RT-bot localization to the sum over fixed points. We have computed the contribution from the trivial connection that one loop determined. And, in principle, what happens when you want to compute the full path integral, you need to get such contributions from all possible fixed points, and you look on the fixed points on the modular space of instantons. Yeah, question.
Yes. Yeah. I mean, we had a really nasty sum on the top over these roots of this infinite dimensional Lie algebra.
This one?
The sum over alpha is the sum that I don't.
No, sorry, it's finite dimensional algebra. No.
So
No,
these are the adjoints of.
I'm sorry. So these
are weights over what?
Okay. Sorry. I'm computing here equivariant Chern character, equivariant with respect to the following torus. Is T2, where T2 acts on R4 with weights epsilon 1, epsilon 2, times T, which is a maximal torus, not in curly G, not in the group of gauge transformation, but in the compact G for which we consider connections.
Right.
So it's finite dimensional. It's finite dimensional guy. So the roots run over.
But I thought so. You made a computation where you explain the appearance of these T1s by computing things only on the omega ones. But these bundles are infinite rank bundles, right?
Wait. These bundles now are finite dimensional bundles.
Oh, then I don't understand what you're taking the tensor product with.
You don't understand what I'm taking?
I thought that you're taking the tensor product of these bundles with the adjoint representation of the gauge group.
Yeah, this is the definition of the bundle, but then
Right.
you have
So
a,
then
right, but then you have an action. You can define action of T2 coming from R4, right?
Yeah, but still, I mean, this is an infinite dimensional guy. You're not going to convince me that T2
Sorry,
is going to get rid of it.
Which is infinite? This guy is infinite dimensional. I agree.
Infinite rank also. So the tensor is a nice guy that is omega I tensor with what?
There is no nice guy here.
Well, okay, so omega I
really.
goes tensor
It's all
with what is the adjoint representation of what?
Oh yeah. This is a G representation of G, of compact G.
Oh, of compact.
Of
So it's
compact
not-
G.
So at every point I thought that this was the curly G.
No. Well, it was at some point curly G, but then it was.
But I thought that these were so when you started doing this computation, it seemed to me that you actually wanted to compute. So this localization procedure brought you from an integral of n equals 2
Right.
to an integral of the Euler class
So-
of this infinite dimension, infinite rank bundles.
That's right. Let me just give you a summary. So I started from integration over the space of all connections, infinite dimensional, quotient by infinite dimensional G. So what I integrate equivariant Euler class with respect to the T2 finite dimensional guy which acts on R4, good, and T subscript compact G,
Okay.
which acts on the space of on this space. Oh, sorry. This infinite dimensional group of G transformation. I forgot to mention that we take it framed. So we take that G at infinity equals to 1. Okay. Then there is compact G which acts on this space. Okay. So we can consider all differential forms or characters or stuff here equivalently with respect to Cartan to maximal torus of compact G.
But the bundle, I thought it was self-dual connections,
So
self-dual two forms, right?
So the bundle was self-dual two forms.
Yes.
I mean, it's just a vector space. The bundle is a product space. So it's the space of self-dual two forms
Tensor. Yeah.
in adjoint of this G is Lie algebra of compact one.
Oh, okay.
Of compact one. This is just like self-dual, fields. This is the bundle where curvature of connection takes value.
Okay.
But this is the gauge group or not?
This is the gauge group.
UN.
in principle, UN, yes, UN, or whatever, or any vision. This G is a compact G. Okay, yeah, and the sum or alphas here is the sum of our roots of the algebra of the compact G.
Sure. Then it's nice.
Good. So Z0 is a product. Sorry, is a product of alpha roots of the compact G of those Barnes functions. Roots of compact G. And these are Barnes functions, generalization of gamma function. They're also connected to quantum dialog.
I think putting this torus, it's your choice. I mean, if you don't put this torus, I mean, the answer is correct, but you cannot move further, right? I mean, you cannot calculate anything. And then you.
It's time.
The chairman is on.
Just one. Oh, okay. So we covered that. One sentence on that. Okay. One sentence. So if you consider S4 and find fixed points of those torus sections on the fields on S4, you will find that it would be north and south pole. And then this localization procedure reduces essentially to convolution of two wave functions which you get around north pole and around south pole. And you glue them together, integrating like by boundary conditions of those wave functions on R4. And that's how you get the partition function in complex spaces. Thank you.
Okay. Maybe we'll take questions in private. So we get a short break before the next.